yeah, there will be some crystal structure as well as supramolecular chemistry. We will talk about lots of non-covalent interactions. So starting from hydrogen bonding interaction, first and hydrogen bonding interaction, and all this. So I am Devashish Havdar, Department of Chemical Sciences, IISc Kolkata, and I am mainly dealing with peptides and peptide mimetic material. So what we are doing in IISc Kolkata, so basically we are synthesizing or developing designer synthetic amino acids and analogs. So these are the representative crystal structure of few of our designer synthetic amino acids. So obviously for most of them there is a chromophoric system, so that we can follow that amino acid by different spectroscopic and microscopic techniques other than crystallography. So what exactly they are doing in biological systems or in material science as well. And then we are using our own developed synthetic amino acid and other markedly available amino acids, so that is coded amino acids, there is a 20 natural amino acids and other non-coded amino acids, some bacterial amino acids. And we are making small peptides and peptide mimetics. And finally we are studying their structures and function. So in function means both in biological domain, biochemistry domain, as well as in material science. But today I will mainly emphasis on material science. So we are handling many projects like that. We are mimicking protein structure and function. So there is a big protein, and in a big protein there are different structure, 2D structure, 3D structure, different domain. We are trying to mimic the protein structure and function using our synthetic peptide. We are also dealing with nanostructured materials, so where we make different kinds of nanomaterials, and then we use the nanomaterials as a delivery vehicle. So if the nanomaterials that is porous in nature, we can put some gas molecule within the nanomaterial depending on the hydrophobicity or hydrophilicity of the cavity. We can put different kind of gas molecule inside that, and then we can use that as a delivery vehicle. And then working on the stimuli responsive gel. So that's nowadays very, very important. So we are now using our stimuli responsive gel for reaction engineering. That's completely a new terminology recently we have introduced. So where the traditional reaction we can perform in a different way. So that is a reaction engineering. And then also these are the traditional works, so like conducting material from this kinds of foldamers, porous organic materials and channels, and little bit of amyloid and its inhibition studies. So we believe that a very small chemical change has huge impact on structure and function of the molecule. So for example, here we have a peptidic material, so, and the compound is nothing but meta-aminobenzoic acid and connected with the NN dicyclohexaneurea, and that point it forms a duplex structure through intermolecular hydrogen bonding reactions. So these are the intermolecular hydrogen bond between CO and NH of two different strands. And then what we have done, we have replaced one of the hydrogen of that meta-aminobenzoic acid with the bromine. And we thought, okay, the bromine is heavier than hydrogen, and so there may be a heavy atom effect, and let's see what is happening. So from the structure, what we have seen that the duplex structure is present, but now there is a CO-Br halogen bond. And due to that halogen bond, the compound is showing phosphorescence at room temperature. So this is really unusual for any organic compound without any metal or anything else that is showing phosphorescence. And we have studied that with all the spectroscopic and microscopic techniques, the compound is showing phosphorescence. Then we thought, okay, so bromine, let's go for a heavier atom. So we replace the bromine with iodine now. And with iodine, surprisingly, there is no halogen bond and no phosphorescence. So from change from proton to bromine to iodine, so there are so much of changes happening. Okay, so then we have incorporated longer oligomer on that series. So instead of one meta-aminobenzoic acid, now two meta-aminobenzoic acid. And what we have seen that these two compounds are showing different structure that we have studied by all the solution state studies, like this 2D NMR, 1D NMR with change of temperature, with solvent titration experiment. So we have studied that they are showing some different kind of structure in CDCl3, chloroform B. And then we got the crystals from chloroform also, and what is seen that when the polymer is the smaller one, so it's forming just a duplex structure, and that through intermolecular hydrogen bond, that's are stabilizing. And in higher order assembly, it's showing some kind of honeycomb type of structure. And this is through intermolecular hydrogen bond stability. But when the molecule is a little bit longer, so that contain two meta-aminobenzoic acid residue, now actually in CDCl3, the two strands, they are intertwined. So they are really making a double helical structure. And that stabilized not only by intermolecular hydrogen bonding interaction between the strand, but also the pi-pi stacking interaction between the aromatic moiety. So the double helical structure is very much stable, and this is the higher order assembly from chloroform, where the double helical structure occurs separately. Now we change the solvent system. So from chloroform to methanol, we have seen a lot of change in the structure. First from solution studies and then from X-ray studies. The same molecule, when we change the solvent system from chloroform to methanol, now it is showing an anti-parallel beta shape-like structure instead of the double helical structure. So it is not only the change in atomic level, but also the change of environment has huge impact on structure and functions of the polymer. Okay. Next, it's a very interesting study. So we have developed a peptide mimetic that can mimic spider cell can wave. So the system is very simple. We have used this leucine and tyrosine, and here we have a diacid. So we just place the leucine and tyrosine in both sides of diacid, and that gives you the three compounds. So in one compound it is both side leucine, in one compound both side tyrosine, and in one compound one side leucine, one side tyrosine. These are three variations, and all are A amino acid. So when it is both side leucine, the compound is crystalline. We have the crystal structure. When it is both side tyrosine, the compound is liquid. In no way you can make it a solid, even using very high vacuum pump for several nights. So it is a liquid compound. But when it is one side tyrosine and one side leucine, so now due to this hydrophobic and hydrophilic balance, the compound is very viscous materials, and it will be viscous liquid above 20 degrees centigrade, but below 20 degrees centigrade it can make a fiber, and then fiber can stand alone like a solid or semi-solid material or a soft material itself. And so using a spatula or a injection syringe, we can make a network of that compound below 20 degrees centigrade like this. So this is a natural spider silk on my window pane, and this is what we have made using a spatula. So the same compound, but if you increase the temperature, immediately everything will collapse. And then we have started with this microscopic techniques, polarized optical microscope, and where we have seen that the synthetic compound, our developed compound, and actual spider silk, they have same kind of optical properties. Also, we have started with geological studies, and we believe that a small chemical change has huge impact on structure and function of molecule, basically the polymers. So, as example, we have developed this compound with meta-aminobenzoic acid and dicyclohexylurea. The compound formed a duplex stabilized by intermolecular hydrogen bond, and then we replace one of the hydrogen with a bromine, a heavy atom. And what we figure out that with bromine, now there is a CO-Br halogen bond, and due to that halogen bond and heavy atom effect, so the compound is now showing phosphorescence. And so we have studied with all the solid and solution phase and microscopic and spectroscopic technique, and that the compound is showing phosphorescence at room temperature, which is very rare for organic compounds. There is no metal or nothing else, it's purely organic compound. And then we thought maybe the iodine will have higher impact, maybe the phosphorescent lifetime will increase, and so we replace the bromine with iodine. But surprisingly, with replacement of iodine, no halogen bond and the compound is not phosphorescence anymore. So, like this change from proton to bromine to iodine, there is huge impact on structure and function of the compound. And then we have developed a larger version of the foldamer, so with 2 meta-aminobenzoic acid in the chain. And from solution state study with NMR, 2D NMR, and then temperature dependent NMR or solvent titration or DMSO-D6 in CDCl3, we figure out that the two compounds are different folding pattern in solution. We have also got the crystal structure of both the compound from CDCl3, and from where you can see that when the foldamer is shorter version, so this is a dimeric structure to intermolecular hydrogen bonding interaction. And finally, in packing diagram, these are also forming a honeycomb-like structure. But for the longer version, when we have 2 meta-aminobenzoic acid residue in the sequence, so actually it forms a duplex double helical structure, and the double helix is stabilized by intermolecular hydrogen bonding interaction between 2 strands as well as pi-pi stacking interaction from the aromatic molecule. And so this is the packing structure of the compound in chloroform. But when we change the solvent from chloroform to methanol, from different solution study, we came to know that the foldamer is now folded in a different manner. In chloroform, it was showing double helical structure, but in methanol now it's showing antiparallel beta sheet-like structure. So we believe that it is not only the molecule, it is the environment that also has huge impact on the structure and function of the material. So then we develop this compound, a peptide mimetic. And so the compound contains 2 amino acids, one is the leucine and another one is the tyrosine, and there is a diacid. So we put both leucine or tyrosine in both sides of the diacid. And in the third compound we put one side leucine and one side tyrosine. So with the leucine, the compound is completely crystalline. So we have the crystal structure. With tyrosine, the compound is solution, it's a liquid. But when we put one side leucine and one side tyrosine, the compound is highly viscous material, above 20 degrees centigrade, but below 20 degrees centigrade it can make a kind of fiber. And so this is the natural spider silk on my window pane, and this is what we have prepared using a spatula, or you can use an injection syringe, and you can do that below 20 degrees centigrade. And also we have studied the morphology of the compound, the optical property of the compound using polarized optic microscope, and where we have seen that both the compound are synthetic material and natural one, they are showing the same behavior. And we have tested with this rheology and then the morphology by AFSM, field emission scanning electron microscope, so which shows that the compound is actually fiber-like nature, and that fiber, if we zoom it, it is actually made of small fibrils. So the fibrils are intended to make the fibers, and that fibers can take some weight. So this is what. And then we have studied the structure of the fiber by using FTIR, NMR, and obviously the X-ray structure. And what we feel that the compound is from antiparallel beta sheet-like structures, and that helps to make a higher order assembly, higher order element than the fiber. So fiber is strong enough to take certain amount of weight, and this actually mimicking the natural structure. And then we have developed a deuterionic spirocyclic mesenchymal complex, And this is basically to remove all kinds of cations and anions from water. So this is the compound which is very simple. So we have just added picric acid with this DCC, N-dicyclic carbodiamide, and immediately it forms a spirocyclic mesenhyma complex. So where we have both positive charge and negative charge on the compound, as well as there are hydrophobic moieties. So the positive charge on the compound will attract the negative charge from the water, and the negative charge of the compound will attract the metal ion from the water. And this hydrophobic part that will actually collect the other hydrophobic pesticides or herbicides or any organic moieties from the water. And by the way, so this compound, if we treat with water, it can clean the water and it's remove any kind of contamination from the water. So we have started with all kinds of metal, and we have seen that it's working very well. And then we use this compound for removal of oils and organic pollutants from water also. And so we have tried with various kind of organic compounds that generally pollute water, starting from different kinds of oil to benzene, toluene, xylene, etc. And we figure out that actually this compound is working fine. And then we have developed a device out of this compound, so to clean up the water or the house of water. So how we develop these things? We have just used a kitchen sponge, the sponge that generally we use to wash the utensils in the kitchen, and we have coated that sponge with our compound. And now if in contact with the oil water mixture, the sponge is actually allowing the oil to pass through, but it's just stops the water to pass through. And so with the oil water mixture, we have added a pump here, and so it's separating the oil from top of the water very nicely. And so by that way, we can use this sponge to clean up water that contain other metal and anion that as a contamination from the water. And that was highlighted in C and E in few years back. So next we have developed another compound that is also a hybrid compound. So this is polyoxysiloxane with an amine functional group here. And this is a very famous dipeptide, diphenylalanine. So this compound is very famous nowadays. A lot of people are working with diphenylalanine because of its hydrophobic galins. So we have this peptide, and then we couple this compound with this peptide. So now it is a hybrid material, organic and inorganic part, both are there. So initially we have studied that hybrid material with different spectroscopic techniques, and we figure out how the molecules self-assemble, what is happening in the self-assembly pattern, and we figure out that actually the molecules of the hybrid material are self-assembled in an antiparallel beta sheet manners, and there is intermolecular hydrogen bond and pi stacking interaction and all these things. But that is the theoretical background. In practicality, what we have seen that when it is only peptide, the compound is showing very nice hexagonal tubular structure. When it is only the inorganic moiety, polyoxysiloxane, this is very nice rhomboidal structure. But once you join them together, this is showing very nice, accurate or very close shape, this microsphere morphology. And these are obviously hydrophobic in nature now, so we have just taken a paper and we coated the paper with this hydrophobic moiety. And now you cannot weight the paper. So if you put the paper in water, again it will come. Without any water, you cannot do that. And we have started by APSM and also by load of the paper, so the paper is now very stronger. And the paper surface is covered with all this microsphere of this compound, so making it very, very hydrophobic in nature. So what you can do with the paper, we have also started with the AFM, the surface of the paper, how it looks like. So now the paper can resist growth of any bacterial colony on the paper surface. So you can use this paper now for wrapping purpose, for packaging purpose, where you want that the water should not go inside and destroy your material, or it can protect your food or something else. So you can use this paper for packing purpose now. Other than that, so now this is iron nails. So we have coated half of the iron nails with our compound, the hybrid material. And we put that iron nails inside a chamber, contain lot of water. So if it is a common iron nail, overnight there will be rust. But when we put that coated part is intact, but non-coated part, the rust forms. So now I can challenge that any raw iron, I can protect it from rusting. So without any very difficult processing. So just coat with this material. This material is completely colorless. You cannot differentiate between them, and you can protect it from rust formation. Not only that, so this is silver addicate. So we know that if you use silver ornaments for a few days, and then in the air there is hydrogen sulfide, the silver will react with hydrogen sulfide, it will turn black after few days. So we have covered the silver addicate again with our material, and now we use inside the hydrogen sulfide chamber, but nothing happens in the cover area. So you can protect your ornament from the silver sulfide formation. Even we have tried in a very harsh condition. So like we put it in the sodium chloride, potassium bromide, sodium. Even in HCl. So when it is coated with HCl, there is no corrosion. But the uncoated part is corroded with HCl. So we think this compound is very effective to protect the material from corrosion. And finally, we have used this compound as a fire retardant. So in 2014, my lab caught fire. Complete lab was damaged, there was nothing. So I lost about 3 crore rupees of instruments. And by that time, I have 12 students. But I promised my student that I will take care, and I have taken care of them. And after that, I have started this research. So I have little information that polyoxysiloxane, it can prevent fire. And then when we have developed this thing, so this is just a mastic. So we have coated half of the mastic with our compound, and then without coating, the mastic is completely bonding. With peptide only, the flame reduces the mastic again completely bond. So with only pause, the polyoxysiloxane, it is reduced flame, but still the mastic is bound. But with our hybrid compound, it stops at the point of coating. So we can take care of fire now with this compound. And we have patented this, and we have a collaboration going on to put this compound as a utility compound in market and future. Okay, so now a little bit difficult or different thing. So this is also peptide mimetics, but now this is discotic peptide mimetics. So it's a disc-like compound. And for that purpose, we have 2 kinds of central core. So one is this triamine or this tricarboxylic acid. And other than that, we can use this dicarboxylic acid amine or this monocarboxylic acid diamine, something like that. But the thing is that when there is 3 amine or 3 acid, this compound is citosymmetric. If you replace one acid with one amine, in a mixed kind of thing, and you lost that citosymmetry. So what is happening with this citosymmetry? How this compound is behaving with change of symmetry? So there was some literature from this Boutalier group. So they have prepared this kind of compound and studied extensively using CD, and they propose that when there is a compound with citosymmetry, that may form a helical structure by intermolecular hydrogen bonding interaction, so on and so on. So we have developed this compound with this benzene tricarboxylic acid, and we have replaced here the acid make a amine, either with methionine or tyrosine. So from solution study we figure out that the compounds are self-assembled in different manner. So when it is methionine, it's something different than tyrosine. And then we got the crystal structure. So from crystal structure it appears that when it is methionine, still the CT symmetry is present. But when it is tyrosine, due to this large hydrophobic interaction, actually two of the tyrosine moiety they are in the one side of the central benzene ring and another tyrosine is opposite side of the central benzene ring. That means theoretically the compound is CT symmetry, but practically you lost the CT symmetry. The compound is not CT symmetry in crystalline state anymore. And then we have checked the central core area. So when it is CT symmetry, this amide bond, they are actually perpendicular to the plane of the central benzene ring. And that helps a threefold intermolecular hydrogen bonding interaction, and finally it forms a columnar structure through intermolecular hydrogen bonding interaction. But when it's lost the CT symmetry, now the amide linkage, they are in the same plane with the benzene ring. And though there are multiple amide linkages, there is no intermolecular hydrogen bond between the amide linkages. Rather than the one molecule is now surrounded by 6 other molecules, and it forms a cage-like structure, a porous structure. And then this is the packing diagram where it shows a honeycomb-like structure, and this is the porous structure. We have also started with the AFM, and which shows that when the compound contains methionine, it's actually from a helical fibrilla structure, but when it's contained the tyrosine, is the porous structure. And we have tested with the nitrogen, and we see that when it is porous structure, it can absorb up to 150 cc per gram nitrogen, which is quite high for organic compounds. So we can make a porous structure just by changing the symmetry of the viscotic tricarboxyamide. And then again, this is something we have played with the viscotic tricarboxyamide, and now instead of aromatic compound, so we have placed with the aliphatic one. So now we placed beta amino acid and gamma amino butyric acid. So with this benzene tricarboxylic acid, and again we see that from UV visible spectra that is following a J type of aggregation. And but when we started in the gelation property, we see that when it is beta amino acid, so it forms a precipitate out of solution, and when it's gamma amino acid, it forms a gel in the solution. So everything is same. There is only one change with the CH2 group, and we are getting two different material properties from this compound. So again, we have started with NMR and with this temperature dependent NMR, and what we have seen that yes, so when it is beta amino acid, there is a different kind of packing. When it is gamma amino acid, there is different kind of packing, and that's why it is showing different. So this is what we are saying. So when it is beta amino acid, so basically it is forming a fiber-like structure, and that fiber further cell assembled by entanglement. But when it is gamma amino acid, it's a straight fibers, and that is not entangled, and that's why we are getting two different structures. And okay, so this is the crystal structure for both these compounds. Once again, here for both the compound, the CT symmetry is lost. So the two of this amino acid functional group is one side of the central benzene ring, and another one in just opposite side of the central benzene ring. But somehow they managed to form a three-member intermolecular hydrogen bond stacking and make a columnar structure. And but in higher order packing, where we have seen that there is a honeycomb-like structure for the beta amino acid, but for gamma amino acid there is this hydrophobic interaction that actually helps to form that molecule gel in different organic solvent, which is missing actually in this case. And then again, this is another example where we have changed the core. with triamine, but this core again it will help to form the gel in different organic solvent, and we have utilized that gel, and from different organic solvent what we get, the thickness and morphology of the fiber is differing from one solvent to another solvent. So it is not only the property of the material, but it is also the property of the environment, how you are changing your solvent, how the solvent is interacting with your molecules, and by that way the gel forms. And here from the APSing, again we see the very dense gel fiber. And then we have studied this gel. This gel is actually forming on sonication. So if you have compound, you dissolve in the organic solvent, you heat it, you cool it, the gel probably not form. But if you sonicate it, immediately the gel will form. And so this is we have studied by CT spectra how the sonication is affecting the backbone conformation for the gel formation. So basically what we believe that in solution you have much more flexibility than in crystal state. So though in the crystal the compound lost its CT symmetry, but in solution when we are sonicating it, the compound get back its CT symmetry, and then it helps to form the fibrilla structure, and which helps the formation of the gel fiber. And so finally we have incorporated this lanthanide nanocrystals in the gel matrix, and we figure out that the lanthanide nanocrystals are finely self-assembled on the surface of the gel fibers, and we use that for a up conversion studies. And so this is something interesting, that with lanthanide nanoparticle, and that is showing the up conversion. Now we have doped with a ketocyanin. So the lanthanide nanoparticle absorption is actually the emission of ketocyanin. So where ketocyanin is emitting, lanthanide nanoparticle is absorbed in that way. So if we just check with a very small amount of ketocyanin and this lanthanide nanoparticle, actually we can arrest that up conversion. And so that is what exactly happening inside the gel matrix. But in solution state, you cannot do that. So in solution state, you have more flexibility, but inside the gel, so you can arrest the up conversion using ketocyanin. Okay. So now in a different story, so we have made an artificial enzyme. So this is the glucosidase. Alpha glucosidase, the main purpose of this, that it can work on carbohydrates, and then it can chop the carbohydrates to monomer. So that is what alpha glucosidase has done. And to mimic that alpha glucosidase, so actually we have developed this tetrapeptide, and that contain phenylalanine alpha amino isobutyric acid. That is a special kind of amino acid, and then leucine, and this is what actually is a Hans ester. We have converted it into an amino acid. And now we have studied the excess structures of this compound. So it forms a hairpin-like of structure. So where we have this two consecutive beta turn structure and followed by a 17-member ring structure. So that is the hairpin structure, very famous motif in protein chemistry. And then we have used this foldamer in presence of iodine, and that actually hydrolyzing the carbohydrates. So for simplicity and to study by spectroscopic technique, so we have just used here this nitrogen. And what we have seen that in presence of iodine just in 12 hours, this compound is chopping this ether linkages, and we are getting this nitrogen, and then you can study with the spectroscopic technique whether it is happening or not. Also we have confirmed for mass spectrometry. But not only that, so we have studied with other carbohydrates, the real carbohydrates, and we see that our synthetic material is working well on the real carbohydrate also, as it is depicted from the mass spectrometry. The main point is that, so once we have done this part, now what is happening to our compound? So the compound, if we go back, we'll see, so there is a hydrogen, and now after this hydrolysis, actually this thing is going to be aromatized. So initially this compound has a angular shape, but when now this is aromatized, so this is just like perpendicular of the two aromatic rings to each other. And that exactly what happened here. So now the beta hairpin structure has lost. So it's a consecutive double bond structure only. Two consecutive beta turn are there, but now the third linkage is lost. The hairpin structure has lost, and the compound is forming a honeycomb-like structure in higher order assembly. So we can use a synthetic material as a parallel of a natural hydrolysis material. And then we have developed this molecular reactor. So the theory behind this is that we will devise a small channel, narrow channel, so where we can put our reagent and we use that confinement to do the reaction further. And this is the scheme. So we have a nano channel. We load component A, we load component B, then we will give some energy, the reaction will happen, and we will get the product. So what is the utility? So this process can be effective for liquid gas or solid gas system. So advantage is this is completely solvent free, eco-friendly, it's energy efficient, there may be some selectivity, and there is a safety and reliability. And so this will reuse basically the organic solvent. In chemistry lab we use a lot of organic solvent, mainly the chlorinated solvent, and finally we claim that we are doing green chemistry, but that is not the part. And simultaneously we cannot stop our reaction, then we will not get our cosmetics, our medicine, anything else. So the main theme was that, so can we do the chemical reaction using less amount of organic solvent or without any organic solvent inside a confined medium? And then for that purpose we have designed this pentapeptide with phenylalanine and alpha amino isobutyric acid at the middle, so 4-phenylalanine. And we have got the crystal structure of the compound, so it's a 3-10 helical structure, completely helical structure. And if we put back the phenylalanine residue, so we'll see actually it's forming a pi channel, so which we can use as a confinement to do our reaction. And next question is it possible? So how we can do that? So first we have loaded toluene in the channel, and we say that 2 toluene molecule is actually going inside the channel. So one is in the channel and another between intermolecular space. But toluene is not very reactive, so it's very difficult to do reaction with toluene. And then we have incorporated aniline. So again 2 aniline molecules just go in the crystal, and so one in the channel and another in the intermolecular space. And now the crystal is light yellow in color, aniline. And this is what the packing structure will be. And now we thought about the reaction. So what kind of reaction we can do with the aniline? So we can do a halogenation reaction that is very simple with aniline. Now the problem is that with a halogenation reaction it can be monohalogenated, and then it will be 3 isomer, or it can be dihalogenated or trihalogenated. So we do not have any restriction on the reaction. So okay, let us start with, and so first we have started with bromination reaction. And what do we figure out that? So when we charge with bromine, the entire crystal structure just rupture. And we are very much frustrated that whatever our hypothesis is does not work. But we have analyzed that debris, and what we figure out that instead of monobromination, it is the tribromination that is happening. And due to this large structure of the tribromination, due to this effect, it's actually ruptured the system, the nano channel. Okay, so then we have done the iodination reaction, and now from mass spectrometry what we have seen that actually monoiodination happened, and our peptide is intact even after monoiodination. So we have so many aromatic rings in the peptide, but only the aniline is going to react with the iodine, and it's the monoiodination happening. And now the question is, so whether this is a orthoiodal or para-iodal, so which form, if there is any selectivity. And what we figured out that though after exposure to iodine, the crystals are very, very bad in shape. So there are huge amount of iodine just absorbed over the crystal, but we just able to take data. The data is not very good, but we figured out the iodine, the what for iodination is taking place. This is because of this particular position of this compound inside the channel. And so we have done other reactions also using this kind of nano reactor, like this Diels-Alder reaction or this Morita-Hilton reaction. So, and this is what we find inside the channel. Okay, and now I came to that gel part, so which is interesting. What now we are saying at that reaction engineering. So for most of the time, so our industry friends, so they said that whatever you are doing in the laboratory that is very fancy, that's with very minimum amount of compound. You are using the chlorinated solvent, which is prohibited in industry, and we cannot use it in industry. So I said, okay, so can we do something that we can do the organic reaction in aqueous medium and in a different way, so that the catalyst we can reuse again and again. And for that purpose, we have developed this peptide. So that's containing again meta-aminobenzoic acid. Here we have a natural amino acid, whether it is the glycine, alanine, or phenylalanine. And then at the end, we have C-terminus ANN dimethylamine as the capping. The peptide is supposed to form this seal-like structure. It will form fiber, and fiber will form gel by restricting solvents. And then we thought, can we use a palladium nanoparticle inside the gel matrix? And so then the entire gel matrix can use for the cross-coupling reaction, like Suzuki coupling reaction. And again, the concept is very simple. So we just put the gel at the bottom, so a layer of the gel at the bottom of a glass container, and then on top we add just aqueous solution of reagent A plus B in NaOH solution in water. And now if the gel is there and on top of there is a aqueous layer, we cannot use a magnetic stirrer. So we have to set the whole reaction system. So it is second, not start. And so after the reaction at room temperature for mild setting of 5 hours, the product will form, and then we will just decant the aqueous layer from top of the organic layer, from top of the gel. And again we will fill up the aqueous layer with the reagent, and that cycle can be continued. So that is what we have planned. So from X-ray crystallography, again this compound that form antiparallel bitter tube-like structure, and finally it forms the fiber, it forms gel in organic solvent. So during gel formation in toluene, so if we use the palladium acetate, the palladium acetate that will interact with the AN and dimethylamine, and it will convert to palladium 0, palladium nanocrystal, and that palladium nanocrystals will covered with the gel surface. So we have started without palladium and with palladium all the rheology and morphology of the gel. And now to how to utilize it. So this is the gel. On top of the gel, we add the aqueous mixture of phenyl boronic acid and this bromobenzoic acid in sodium hydroxide little bit. So that is our reaction medium on top of the gel, and the palladium are actually in the gel. And now we are setting it with little bit for 5 hours, and so the boronic acid and bromobenzoic acid will react, and that will form the compound. And once the compound forms, we just decant the aqueous layer, and we acidified the aqueous layer, we got back the product, and we separate the product by filtration. And again we can top up with the reagent, and we can do the reaction. So we have done this reaction up to 5 cycles with almost 70% yield up to 5 cycles, which is not bad. Because every time when we are decanting, there is possibility of some leaching of the palladium nanoparticle from the gel matrix. And this is what the substrate scope. So we can do this with the brominated compound, with the iodobenzene, or with the pyridine unit as well. So we have a lot of substrate scope for this kind of reaction. So same catalyst we can use for multiple time. We can do the Swinubie coupling reaction at room temperature and in mild condition without stirring, it's just a setting. And we can easily identify the product simply by acidification and then filtration. Okay. And then this is my colleague Biplav. So he has reported this reaction intermolecular D-aromatic 4+2 cycloaddition of naphthalene visible light energy transfer catalysis. So initially when Biplav showed this result, I don't believe, because the naphthalene cannot do this sort of reaction. Here we have naphthalene that is the aromatic stability. If it's going to do this reaction, then it has to lose the aromatic stability. And why it will go for that? But actually Biplav proved that it's happening. So with the photosynthesizer and then in methyl cyanide, acetonitrile, room temperature 24 hours with the blue LED. So this reaction is happening. This naphthalene derivative is reacting with this, going for a disulfide reaction. From a two-dimensional structure, it is forming a three-dimensional structure. And what Biplav mentioned in his paper, so this is actually the stability of the transition state. So if you can make the transition state stable, then the reaction can happen. And how to make the transition state stable? Now, if you avoid oxygen. So actually for most of the reaction, oxygen is the culprit. So that's attack the transition state and that demolish the transition state, and that's why the reaction not happen. And so what Biplav used, they use very inert atmosphere to do this reaction. And then I said, and they have done all these optimization studies and they have reported this. And then I think, so can we do this reaction without any inert atmosphere in a confinement inside the gel? So for that purpose, particularly we have developed this gel. So now the gel, there is no aromatic ring, nothing to absorb light. So with our gelator, we make gel, it's forming gel in DMSO, DMA, methanol, acetonitrile, kerosene, hexane, and then we have started with the rheology. So the gel is forming fantastic. So it, from the morphology, it's fibrous in nature. Also, we have studied the melting point of the gel, and what we have seen that with increasing gelator concentration, so if the gel is very, very concentrated one, the melting point is going to be increased. And the gel has very good self-healing property. That means if the gel we cut in pieces and again we put together, they will self-heal. They will make a single bar or single fiber from the gel. And so then we thought, okay, let's do the reaction. So this is we have taken our gelator in acetonitrile. Just we use that acetonitrile from our solvent purification system, and no degashing, nothing. And then we have used our material, all put them together with this catalyst, and then we just sonicate it. So immediately it forms gel, and due to this catalyst, so now it looks like a little bit yellow, otherwise the gel is white in color. After 24 hours, 440 nanometer light, so the gel actually made. And so we realized that something is happening with the gel. So we analyze and we figure out that yes, the reaction is happening. So say now this is open tube, so test tube. So it is open here. The so sensitive reaction is happening in the gel matrix, and gel matrix is working as a confinement to do this reaction. So we have started with all the rheological systems. So before incorporation of the reagent, after incorporation of the reagent, after the reaction, how the viscosity and rheology of the gel is changing. And then we have optimized with the concentration of the gelator, and we figure out that at 25 milligram per ml gel concentration, the reaction is happening very nicely. And under open air, we are getting 68% conversion, which is quite good. And so we have also optimized with the gelator concentration, and what I have said that at 25% gel concentration, the reaction is happening nicely. Again, we have started with different solvent, and even now with methanol, we are getting 60% conversion. So if you are just taking acetonitrile in solution, there is no product formation. But inside gel, even in methanol DMSO, we are getting a very good yield. And finally, we have optimized wavelength, and we have seen that 456 nanometer is not working that well, but 430 nanometer light, the reaction is going very, very well. And so we have started with the different substrate scope, and this reaction is happening with different substrates, almost 68 to 72, 73% product in some cases. And then we have studied the morphology of the gel before and after reaction. So this is the undoped gel, so that is only gelator. And then with the photocatalyst and the substrate, so the gel is looks like that. After light irradiation, when the gel melted, so it looks like that. That means once the gel melted, basically our reagents are exposed to the air, and by that time oxygen is killing the reaction. And so we are stopping at 68% product. But if we can protect it, maybe with some other gelator or maybe with the high concentration of gel, the reaction can go up to 90-95% of yield. Because in solution state, the oxygen will intervene and it will kill the activation state, and it will stop the reaction. And then this is the final one, so where we have seen this paper from Burkhardt group. So they have used organic semiconductor photocatalyst for bifunctionalized of arenes and metal arenes. And basically this is the photocatalyst G3N4, what they have used for this kind of reaction. And then the reaction they have done basically this cyclization and followed by this CF3 installation on the arenes. And so this is the substrate scope what we have seen, and this is what it. And then another group from China. So they have used this same catalyst, photocatalyst, for conversion of ethane to ethanol, just using hydrogen peroxide and the palladium particles inside the photocatalyst. So this is the G3N4. We thought, so can we do this kind of photocatalysis with our gel system and do more or better reaction? So we have made that photocatalyst. We have studied with all the spectroscopic techniques, the state of the photocatalyst. Then we have made this gelator, again, different kind of. Similarly, this gelator, they do not have any aromatic system, so it cannot absorb light. It forms gel in different solvent like DMSO, DMA, methanol, acetonitrile. We have studied the gel with rheology, so the gel is very fine. Gel is also showing the self-healing nature, and this is the morphology of the gel. So it's almost like a Maggi noodles, so very much entangled gel fiber. The confinement are very good. So then we have done this reaction with the help of my colleague Suresh Devaraju. So the photocatalyst G3N4, CF3SO2Na, 2 equivalent in acetonitrile and 456 of room temperature 24 hours. So the reaction is happening, so this is cyclization and followed by this CF3 installation on this part. So when this is in oxygen without gel, so there are almost no reaction. In open air, almost no reaction. But in presence of gel, we are getting 95% in open air. So that means oxygen cannot permeate through the gel, and the gel acts as a confinement, and gel can do this reaction, and we are getting 95%. So very clean reaction. If we compare from the previous one and this one, so in previous one, a 2D molecule has converted to a 3D molecule, and due to this size exclusion, actually it's ruptured the gel fiber, and the gel made to solution state, and then oxygen intervened and stopped the reaction. But here, there is no such three-dimensional molecule, so the gel fiber is intact, and so we are getting reaction with 95% conversion. So we have done with all the optimization with different photocatalysts, and what we figure out that GCGN4, that photocatalyst is working fine. We have also tested with many solvents, and acetonitrile we are getting very nice product, 94-95% yield. And this is what happening. So this is the gel containing the reagent, all the reagent. And after the light irradiation, the gel is intact, and that's why we are getting 95% conversion. And so this is the morphology of the gel and the reagents before reaction. This is after reaction. So the morphology of the gel almost intact. And we have started with rheology before gelation, after gelation, and before doping, after doping with the reagent, and after irradiation of the light. And so this is the substrate scope. So we can do this reaction with many substrates, and that are giving very nice yield. Okay, so with confinement, now we can actually engineer our old reactions that need very sophisticated laboratory environment like glove box, like inert atmosphere, or any other sophisticated hood or something. But you do not need that at all. Actually, in an open table, if you have things, so just make a gel and put a blue light, you will get your product for all these sophisticated reactions. And so this is my research group, so who have students who have done this whole thing. And for financial support, CSIR, DSP, World Foundation, and Ananda. And thank you very much for listening. If you have any questions,
Any questions?
I have.
yeah, yes, sure.
It's a very nice, very nice demo. So, what's the concentration you have to use in order for gelation? So, percentage.
Generally, if we report for only gelation, it is 2 milligram per ml, so which is very, very less. Even for some gelator, it is 1 milligram per ml.
Yes.
But for this kind of reaction within gel,
Yes.
we have to use a higher percentage of gelator.
Yeah.
Otherwise, though we claim that we are using UV light and we are using fans, so it is not heating. But even UV light heat your gelator, there some temperature increases and gel may melt.
Yes.
So that's why we use a higher gelator
Yeah,
concentration.
you need a stronger
Strong
gelator for
gelator,
that.
yes.
Very nice. Very nice work. Thanks a lot.
Yeah, this is very nice talk. I have a question regarding your breaking of gels, right?
Yeah.
So when you break the gels, do you see transition to colloidal system, like do you form colloids or crystals when you break the gels?
No, it's actually from gel state to solution state. So not colloid, so something precipitated out, and the acetonitrile is on top of that thing. So that is what happening. And if something is soluble in acetonitrile, so little bit of gelator soluble in acetonitrile, so it's done. So it's not a colloidal one. And it's easy to separate the product from the reaction inside the gel, because the gel is very, very hydrophobic in nature. It's soluble in hexane and some hydrophobic solvent. And our product is not soluble in that. So you just use different solvent system, very easy to separate the product and purification. And if you can separate the product, you can reuse the catalyst for multiple times.
Sir, I'm Priyasha Tiwari. I'm from Scottish Church College. Sir, you said that fiber is strong enough to contain weight. So, spider-like wave, when the compound is one side tyrosine and one side leucine, more than 20 degrees Celsius, it's a 5. So, below 20 degrees Celsius, is less stable than.
No, just reverse. So more 20 degrees centigrade, it's collapsed. So it forms a liquid, viscous liquid. So below 20 degrees centigrade, it forms the fiber. So if you have experience to walking in the morning in garden, mainly in the winter time, you will see in the early morning there are a lot of this spider web in your garden. But at 8 o'clock or 10 o'clock when the sun rises, so everything disappears. So it is the same type of material. So at temperature above certain temperature, it will collapse and it will form a viscous liquid. But below 20 degrees centigrade, so it will form the fiber. And once it is fiber, it can take some weight, like the spider net. So the spider can move from one side to another side, or something big catch, it can be stuck in the spider net. Yeah. Any more questions? Thank you very much.